Yeah, so this is joint work with Gowtham Kaki, my advisor, and Evan Chang at CU Boulder. So if you've been, If you've been at the conference all week, you've probably heard one or more people shout that distributed systems are hard, and it is absolutely true. The more specific claim that safety verification for distributed systems is hard is also true. So why is this? Well, a big part of the problem is that verification in the distributed context takes a bird's eye view. We're looking at global states of the entire network. That means arrays of node states, sets of messages in flight. And that means that we end up with big inductive invariants that have to discuss all those states, relate every message in flight with some state that it came from. It means that it's hard to automate. We have things like arrays, which are not great for decidable fragments. And it's all kind of frustrating because most of this is a model. It's not really the actual code of the system. It's the sort of model of the network, which isn't really the part that's unique to you. The specific code is way down at the worm level, running on a single node, processing a single node state and a single message at a time. So what can we do about this? Well, in this talk, I'll tell you about how for consensus algorithms, we can actually do verification at the worm level. So from the worm's eye view, we can verify by implementing the consensus algorithm using causal replication, by specifying it, the consensus safety property, which is a global property, using the local properties of monotonicity of individual node states and commutativity of messages. And by verifying this using a inductive verification artifact called a stable update precondition. So this is basically the outline of the talk. And then I'll talk about our case study, where we've applied this to a real useful consensus protocol that works like Raft. So yeah, what is a consensus protocol? You might be asking. Here's an example, the party planning protocol. So the point of this protocol is to determine a location for a party. So at the beginning, nodes have no idea where the party will be. Eventually, they learn a location. And what we're trying to avoid is having nodes learn conflicting locations. At that point, safety is violated. You split the party. You might have people show up at different houses, and that's no fun. So the way that this works is nodes sort of run a little election where they pick a unique leader. And so every time one votes, it's broadcasting that message. We're in the causal replicated paradigm here. Once a node has seen that it has received a majority of votes, then it's the leader, and it can pick a party location and broadcast that to the other members. Now, this is causal replication, so that means messages are delivered in like a causal order. So green here, for example, can't learn about the party location until it's seen the vote from purple that enabled blue to actually make the decision. That'll become important in a minute. OK, so how do we verify this then? We can think of our basic inductive verification step is going to look at some event on a node that's starting in a state, processing some code, and ending in a state. And of course, the problem, as I talked about with the bird's eye view, is that the safety of that final state kind of depends on the other states of the other nodes. And even worse, when this event is probably the delivery of a message, an update, and we're going to run some code on it. But where did that update come from? That's going to depend whether it's actually possible to receive it in this state. And even worse, we have an asynchronous system. So really, the update's coming from some kind of like in-flight message queue, and now that's part of the state. And so our safety is going to have to discuss like those messages as well. So again, it's going to get big, and we want to avoid this. So the first thing we're going to handle here is safety. We don't want this global notion of safety. So let's think about a slightly weaker property than consensus safety. This is convergence, a property that's going to be familiar to anyone who's worked with CRDTs. The idea is that eventually all the nodes, under some conditions, can arrive at the same state. In this case, they'll know the same location or no location. OK. So this is not our consensus property. It does allow, in the meantime, nodes to have different locations. And as we saw, if that ever happens, then you could end up with different people at different houses. And so we need to avoid that. So convergence is not enough on its own, but it becomes enough if we add monotonicity. So here, once a node learns a location, it cannot unlearn it. So this is just a relation on individual node states. And once we add this in, we can see that if we have these different node states, or these different locations A and B, that eventually transition to the same location C, if they're following the monotonicity order, that's not possible, and so they would actually have to be the same. So we can get consensus from monotonicity and convergence, and again, for the CRDT folks, convergence we can get from commutativity on pairs of messages. So we have two local properties, monotonicity on pairs of node states and commutativity on pairs of messages. OK, this is great, but we still need to deal with this, where do the messages come from? What kind of context do we have for those? So the way we're going to deal with that is with a verification artifact called the stable update precondition. So this is just a precondition on updates. So if a node generates an update, its local state has to have satisfied the precondition. So for the announcement that the party will be at 44th Street, the precondition would be that blue has to have recorded a quorum of votes for itself, and its own location has to be none. It can't have picked a location yet, otherwise that would violate the monotonicity that we just talked about. So great, that makes sense. Now we extend this to the notion, the stronger notion of a stable update precondition by saying that it's stable if it's also true for every node state that this update gets delivered into. So purple here would also need to know that quorum of votes for blue, and also its own location would be none. So we're going to inductively verify these, and the base case is pretty simple. It's just whatever code is running on blue that's generating this announcement had better satisfy these properties. But the inductive case, what does that look like? So we could think of this as, suppose there's a message, an update, that is in flight and it's ready to be delivered into state S. So S must satisfy its precondition, that's our inductive hypothesis. But now interference occurs. Another update gets applied to S. So we actually have to show that if S satisfied the precondition of the blue's update, then this new state will have to as well. But we can depend on the fact that for purple's update to have been applied to S, S also had to satisfy its precondition. So if purple's update was a conflicting announcement, that means that S would have to contain a majority of votes for both blue and purple, which can't happen. So we don't have to show that blue's update would still need to hold in that case. That's not possible. OK, so that's basically how we're going to get this stability. And that will help us, obviously, with monotonicity, because we just consider that any state that an update applies to has to satisfy the precondition, and then we can get monotonicity. Commutativity is a little different. So we care about commutativity when there are two concurrent messages. So that means that they're both in flight, they're both headed for the same state, they're essentially racing towards that state, and we don't know which one's going to apply first. So in this case, we need to show that it doesn't matter which order they apply in. But just like with our previous verification condition, we can depend on the fact that the state that they're both about to be delivered into has to satisfy both of their preconditions. So again, if we're talking about two conflicting announcements, it can't actually satisfy both of their preconditions, and so we don't have to consider those to be commutative. So this is called racing state commutativity in the sense that it only matters for states in which two updates are racing towards. OK, so to finish up, I'll talk a bit about our sort of case study of scaling this up to a real consensus protocol. Raft-like in the sense that it has the same interface and safety guarantee as Raft. So this is called Fairy, kind of a pun on Raft. Interesting sort of implementation details. It maintains these trees of logs instead of single logs, which allows you to avoid retransmission. Talk to me later if you're curious about the details. But it's implemented in Haskell on top of a causal replication layer, as I've described. Verification for it was able to fit into extended EPR, so all the verification conditions are decidable, and the verification artifacts, like the stable update preconditions, size up to about 110 lines of code. An interesting bit on the causal replication is that it simplifies the design of Fairy compared to Raft. So in Raft, there's this important detail that when a follower votes for a leader, the leader has to find out about all of the followers, all the log entries that the follower has seen before it can actually become the leader. And in Fairy, the causal delivery just does this for us. And so we don't actually need to specify this in the code of Fairy. So we did a performance comparison to sort of the leading industrial implementation of Raft, etcd, to see if this causal delivery thing is going to slow us down. So this is etcd in blue, and this is Fairy in green. So we actually outperformed it on a cluster of 5 machines. And I think there's a couple possible reasons for that. Again, if you're curious, talk to me. But the important thing here is that the causal broadcast did not slow us down. OK, so basically, just very high-level picture here. We're stacking strong replication, a consensus algorithm, Fairy, on top of causal replication, hence bolting it on. This is not really something that's been done before. In the past, these have been kind of seen as and implemented as sort of separate domains. So that's kind of interesting. In conclusion, I've talked about a new style of verification for consensus algorithms, which is enabled by our discovery of the derivation of consensus from monotonicity and commutativity. It's enabled by our new inductive verification artifact, stable update precondition, and it works in practice for a Raft-like algorithm. So that is my talk. Thank you for attending. Ask me questions.
Please come up to the mic if you want to ask questions. And may I ask the next speaker to come set up? Yeah.
Hello. Thanks so much for the interesting talk. So I was thinking about 2 properties of consensus. One is no duplication, and the other one is termination. So
okay.
No duplication, if you keep receiving things as you go, when you're receiving multiple times. And then also for termination, if everyone votes for himself, there will not be a leader to broadcast to everyone.
Right, yeah.
So I was wondering what these 2, but again, thanks so much for the talk.
Yeah. So the no duplication, we assume that is part of the causal message delivery system. So that's part of the message layer. The termination, we're not verifying termination, but so the toy sort of example I showed you does not necessarily terminate. There might be a tie, and then the party never happens. But for Fairy, like Raft, we get this sort of probabilistic termination where new elections can start after random timeouts, and so eventually, in practice, we will have termination. Thanks.
A quick question. Oops.
Yes.
Quick question. This is pen and paper verification of the Fairy protocol, right?
So
have you, or are you thinking of
OK, so I mean, the soundness of the sort of inductive verification technique with the strong update preconditions is pen and paper. Given that, then the verification of Fairy is automated using an SMT solver.
so,
yeah.
okay.
Thank you.
Let's thank the speaker again.